Okay, part C of the circular motion. We're now going to get into the application and look at the optimum banking angle derivation. Okay, so you may have noticed that many racetracks have banked curves, cycling velodromes have banked curves, even freeways and motorways often where they have curves have banked corners. And you may or may not have wondered, well, what is the purpose of those banked corners? So what we're going to do here is firstly explain the purpose of those banked corners, and then secondly work out if we're designing a road, that what angle do we need to bank that corner at to make it, well, in essence, as safe as possible. So previously we learned, when we go around a corner, we can rely on friction between the tyres and the road to provide the force to cause the centripetal acceleration to turn the car. But obviously, if roads get wet, or in some parts of the world, if they get icy or they get oil spilled on them, then we lose that friction. We lose that frictional force between the tyres and the road. And in those cases, a car can obviously not turn and keep going straight ahead and basically what we'd probably call spin out off the road. So by designing a banked corner, we minimise or eliminate the possibility of that happening. So how does that happen? Well, firstly, any object on the surface of the earth exerts a weight force downwards. So that weight force is equal to its mass times the acceleration due to gravity. Now, something interesting happens here. When one object, Newton's third law says when one object exerts a force on the other exerts an equal and opposite force. So the car exerts a force down on the road due to its weight, but that equal and opposite force, which is what we now call that normal force, is directed perpendicular to the road. So the normal force, the equal and opposite, is directed not straight back up, but at 90 degrees to the surface of the road. So normal, it's another word for a right angle, or something at a right angle, so we call that the normal force. So now we have this normal force directed in, or like this, we can see that has two components. It has a vertical component. So there's a vertical component that stops the car from sliding down the road or sliding back up the road if it's too great. But we also have this horizontal component which goes towards the centre of the circle. So this horizontal component towards the centre of the circle is what can cause our centripetal acceleration. So let's explore that in some more detail. This is actually the derivation for the optimum banking angle, which is over here, is one of the derivations that you need to know. Now it's quite a long derivation, which is why I've sort of typed this one up rather than handwrite it as I go. And to be honest, you rarely get asked to do this whole derivation. Normally you will get asked just to do a part of it, or given a part of it, finish it off, or it's something that you're led through. Theoretically, you could be asked for the whole derivation, but as I said, that's rare. So let's work our way through, starting with this diagram that we just looked at. So we've got our weight force of the car exerting a weight force down on the road, and that's sort of described here. The road exerts an equal and opposite force on the car, but that's at 90 degrees to the road, at a normal to the road. So we call that our normal force here in purple. That normal force has a vertical component up here, and we can use a bit of trig and go, well, this is our, if this is our banking angle, this angle here is 90, this angle here is 90 minus theta, this angle here is 90, there's 180 degrees in a straight line, so that angle here must also be theta. It's equal to 180 minus 90 minus 90 minus theta, minus theta is equal to theta. Do the trig there if you're not sure and you want to convince yourself. So, from trig we can see that the cosine of this angle will equal the adjacent over the hypotenuse, so it will equal the vertical force over the normal force. we can rearrange that to find out what the vertical component is with relation to the normal force. And using the sign relationship, opposite over hypotenuse, we can do a similar thing to work out what the magnitude of the horizontal component will be with relation to the normal force and the banking angle. So normal force, banking angle. So let's think about this situation. The force causing centripetal acceleration for a car rounding a banked corner, FC, can come from either friction between the tyres and road or the horizontal component of the normal force, FH. That is, the force to cause centripetal acceleration is equal to the frictional force plus the horizontal component of the normal force. At the optimum banking angle, there is no reliance on friction. So we can assume that the frictional force would be 0, and all the force causing centripetal acceleration comes from the horizontal component of the normal force. That is, FC is all coming from FH. So FC, we talked about this in the last 2 slides back, I think, is force is mass times acceleration. The acceleration is v squared on r. So we get this relationship mv squared on r, which is this force to the centre, which causes circular motion, is equal to the horizontal component of the normal force. Okay, let's think about the vertical direction. For there to be no vertical movement of the car, i.e. it's not sliding up the hill or sliding down the hill, the weight force and the vertical component of the normal force must be equal and opposite. So that force there, the vertical force, must be equal and opposite to the weight force. If this is greater, the car's going to want to push up the hill. If this is less, the car's going to want to slide down the hill. So when they're equal, the weight force equals the vertical component of the normal force. So if we substitute, the weight force is mass times acceleration due to gravity, so mg is equal to the vertical component of the normal force, which we showed how we work out over here, Fn cos theta. We can rearrange that and we get that the normal force is equal to mass times gravity divided by cos theta. Then we substitute equation 2, so we substitute this equation here into this equation we worked out over here, and in particular into this end part of this, mv squared on r equals fn sine theta. So mv squared equals fn equals mg divided cos theta, so that there comes from there, times by sine theta. We've got mass on both sides, so they cancel out. We want to get rid of g on this side, so we divide both sides by g, that and that cancel out, and we get left with v squared on rg equals sine theta on cos theta. And for those of you who have done any trig would remember that sine theta on cos theta is equal to tan theta. So we've shown tan theta equals v squared on r. That is our optimum banking angle. Fair bit of working out to get through that one. I suggest you watch this one over 2 or 3 times, and then I suggest you actually have a go at doing this derivation yourself. Some of the questions, obviously, as you go through in the book and the assignment, will also ask you to have a go at this. But it's really, as much as anything, it's an exercise in trigonometry with a little bit of algebra. Obviously with a little bit of the understanding of the physics. But setting up this diagram, I think once you get this diagram set up, it all follows quite easily. Okay, you'll also see an alternative derivation sometimes for the circular motion, which I will briefly mention. I prefer the way I've done it, but you do sometimes see this other way, so I will briefly explain that as well. And that basically works on the principle that we've got our angle here, theta. Our horizontal component here, if at the optimum banking angle that horizontal component provides all of the force that we need for circular motion. So we talked about that just there. So that force is mv squared on r at the optimum banking angle. And also at the optimum banking angle, the vertical component of the the vertical component here of the normal force must balance out the weight force, so that the car doesn't, if this was greater, the car would go up, slide up the hill. If it was less, the car would slide down the hill. So these two must be equal. So the weight force is equal to mass times gravity. So the weight force at the optimum banking angle must be equal to mass times gravity. I think I just said weight times gravity, but the weight force is equal to mass times gravity. So that means our opposite becomes mv squared on r, our adjacent becomes mg. Tan theta equals, let's colour code it, equals opposite over adjacent, which is equal to, our opposite is equal to the horizontal component of the normal force, and our adjacent is equal to the vertical component of the normal force. And as I've just said, at the optimum banking angle, the horizontal component is equal to mv squared on r, and the vertical component is equal to the weight force mass times gravity. So if we cancel those m's, we can see that we get left with tan theta equals v squared on r times g. So we get the same relationship as over here. So that way maybe is a little bit simpler. I don't think it's as thorough and logical though as the first way, but I'll point them out as both because you may see both around the place. But once again, look over the video a couple of times, do some questions, make sure you're comfortable with this derivation.